Good day, learners. Welcome to Technical Sciences lesson. My name is Zamisile Mdima. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. Okay, so today we're looking at revision once more. However, today we're putting our focus more on the resolution of force into components, okay? Vertical and horizontal component that is, as well as we're going to be looking more into frictional force, okay? How to calculate frictional force and all of that. So welcome to today's lesson. Let's begin. So let's look at our pillars that we're going to be focusing on once more. We are doing mechanics revision and we're going to be looking at resolution of force into components. Here's our frictional force over there, and we're going to be sharing problem solving strategies. Okay. Remember, by now, there's knowledge that we should know based on our previous lessons. I'm going to go through them a little bit so that we remind ourselves even on chapters that we're not going to be zooming on today. However, on the prior knowledge that by now we should be knowing. Okay. Now, by now, we should know the difference between vectors and scalars, okay? And also know how to graphically represent the vectors. Remember, your vector has to have an arrow, so it's a line with an arrowhead, signifying your direction, as well as the magnitude of that vector, because a vector has to have a magnitude as well as direction, okay? So, the longer the length of the line, the more or the bigger the size or rather the magnitude of that specific vector, okay? Even if you're drawing it in scale or out of scale, it should be a representation of that specific vector. And then by now, we should know the kinds and types of forces that they are. Remember, we've got the contact as well as got the non-contact forces. Contact with the ones that we have a physical interaction with, okay, like when you are applying a force, applied forces, and then your non-contact forces such as your gravitational force, because gravitational force does not need to exactly touch a specific object for it to be exerted on the object, okay? Also, by now, we should know the sign conversions. What do you mean by that? Different methods of representing the vectors. For example, we've got your Cartesian coordinate system, you've got your compass directions, you've got your bearing. Okay, now Cartesian coordinate system uses lines on the Cartesian plane, such as your x, which is your horizontal, as well as your y, which is your vertical. Okay, compass direction makes use of your north, south, west, east, your northeast, all of those compass directions. So they might give you the direction of the vector, but in a compass direction. So you have to know when we say northeast, where exactly is that vector facing? Okay, bearing, that means we're making use of what? We're going to be using a protractor so that we are able to determine whether the vector is on the first quadrant, the second quadrant, the third quadrant, or rather the fourth quadrant. Remembering the fact that your north is your reference point, meaning that that's where you're starting, and that how we start calculating is in a clockwise direction, meaning you have your north over there right at the top and you move in a clockwise direction, okay? And then difference between collinear and coplanar vectors. We should know the difference between the two by now. What is a collinear vector and what is a coplanar vector? Okay, well, your collinear vectors, and we should be able to point out that this is your collinear vector and this is your coplanar vector. Okay, same line of action or same plane. And then by now, we should be able to determine the resultant force using Pythagoras theorem, your head-to-tail method, your parallelogram law of forces. So utilizing all these three methods, you are able to find or to be able to determine your resultant force. Okay? Resolution of force into vertical and horizontal components. Remember, this is what we are zooming in for our revision for today, as well as we're looking at frictional force. Remember, there are different types of frictional force. We've got your static frictional force, and then we've got your kinetic frictional force. Not forgetting the definition of a kinetic frictional, your definition of a frictional force as a whole. That is, it's a force that is parallel to the surface, and it always opposes the motion of the object. Okay, but now when it's static, it's a frictional force that acts between two surfaces when an object is stationary. Okay, when we say the object is stationary, it means that the object is at rest, it is not moving. Okay, your acceleration is 0. Okay, and when the object is moving, that's when we're gonna have your kinetic frictional force, whereby it is the frictional force that acts between two surfaces when the object is moving. Okay, and it's very important to have frictional force in our daily lives. We're going to be reminding ourselves on that as well. So this is the information that we've covered on our previous lessons. However, today we are going to zoom in on the resolution, which is your second last bullet, which is your resolution of force into vertical and horizontal components. We are just going to team it up with frictional forces so that you're going to find in one question any of the two, so that we know how to respond to them. We know we share strategies on how to respond perfectly and all of that. So let's dive into it. So we've got our question, and then we're going to have a separate paper or page whereby we're going to be sharing the strategies on how to respond to such questions. Okay, so the first question we have here is on mechanics revision. Question 1 is saying two forces, F1 and F2, keep the object of mass m stationary as shown below. Okay, so I've got F1, which is equals to 150 newtons, acting at an angle of 30 degrees to the vertical. Okay, and then we've got F2 that acts at an angle of 22 degrees with the vertical. Remember, it is important to read the statements that you are given, because that's where the most information is at. Okay, so let's look at the diagram. I love it one because now they give us a description of what is happening, also giving us a diagrammatic representation of what it is talked about. So here's our mass m. It's an unknown mass, and we have F1 as well as we have what, F2. Okay, so the first question is saying calculate the force F2 using the horizontal components F1 as well as what, as well as F2. Remember that we've got F1 that is given to us as what, is 150. However, our F2 is not given to us. So what are we supposed to do with this one? Okay, so we've got a blank paper where we're going to be writing our solutions. So I'm going to say solutions for question 1. Okay, we are specifically looking at question 1.1, and we want to find the magnitude of the force F2 using the horizontal component of F1 as well as F2. Okay, so I'm going to get my calculator ready because I am going to need it. I hope you are ready with yours as well. So let's get down to it. So with here, if you split it like this, because this is 30 degrees to the, okay, but now the angle that we are interested in is this one, to the horizontal. Okay, so assuming that this part is making what, a 90. So what is that angle that is F1 acting to the horizontal? Okay, so 90 minus 30 is going to give us 60. That means this angle over here, it is 60 degrees to the horizontal. Okay, so now let's go find out for F1, because these ones, the horizontal forces are balanced. So if we can find the horizontal component for F1, that means we'll know for one in what, in F2. Okay, so we say we have F1 x, because we're looking for the horizontal component for F1, okay, is equals to F1 cos of theta. Okay, so what is the magnitude? I'm going to go back and forth a little bit so that we get a glimpse of what we're talking about. So we've got F1 having a magnitude of what? Of 150. That means over here we've got 150 cos of 60 degrees. Okay, so what is then now 150 cos of 60 degrees? Okay, punch it in your calculator, is going to give you 75. That means the horizontal component, 75 what? Newtons. Okay, what does this tell me? Because now there is a mass that is hanging, balancing the two forces. If I know for F1x, I also know for what? For F1, for the other one as well. Okay, so this one will be, so therefore F1x is therefore equals to F2x. Okay, however, I still don't know which one it is for F2. Okay, because now I haven't calculated the force F2, so that's what I have to do. So therefore, if this is 75, therefore this is going to be F cos, okay, of what? Let's go back a little bit. We've got 22, okay? So 22, we're not interested in this 22. We are only interested in the angle between the what? The horizontal. So in that angle, what is that angle in there? It's 68, right? So if our F2 then is equals to the main one, which is then cos of what? Of 68 degrees. And why do we have a 68? Okay, remember here we're saying if F1x is equals to then F2x, that means both of them are what? Are 75. Okay, so why are we doing that on the side? So that we are able to find the magnitude of what? Of the main force, which is your what? Your F2. Let's just write F2 over here. So this one, why are we saying this? Let's go back a little bit. It is because your forces in the horizontal, they are balanced. Okay, so therefore we're saying horizontal forces horizontal forces are balanced. Hence, we say if we know the horizontal component for F1, that will be equals to the other one. So now let's try and resolve and find the main force. Okay, so if your F2x now, it is 75. Okay, therefore we have an unknown of F2. And cos of what? And cos of 68 degrees. Okay, so now we only have one unknown. So what is your cos of 68? Cos of 68 is going to give you, this is, we take it down as it is, so it's going to give you 0.37, and then over here we get down with our 75, okay, because we want to find F2 and not F2 0.37, so we're going to divide by 0.37 on both sides. Okay, that, use a different pen so that you are able to tell which number it was before then. So what is then now 75 divided by 0.37? it's going to be 200. Just write it nicely. 202,7 is equals to F2. Okay, therefore F2 is therefore equals to 202,7 newtons. Don't forget your units. Units are very important. They specify what you are talking about. Okay, so that's how we do the 1.1, where we say calculate the force F2 using the horizontal components of F1 as well as what? As well as F2. Okay, so what we've done is that we have used the components so that we are able to find the main force of F2, because F2 on this side was not given. Okay, so that's how we do it. So calculate now the mass of the object. Remember, this mass is hanging, so it's moving alongside the what? The vertical, right? Let me try and find some space in here. Okay, let me use a different pen so that you are able to separate 1.1 from 1.2. So with your 1.2, because it is hanging, so now the forces that are keeping it hanged are the vertical components, okay, alongside with gravity that is trying to pull it out. So these two are acting against each other. Okay, so what we first need to do is to find the F net for the vertical components and then equate it to gravitational force. Okay, because it's neither falling down or it's neither going up. Okay, so look at the diagram as well. So what we should be doing over here is that we have to find F1y. Now, F1y is going to be F sine theta, okay? Because now we're talking about the vertical components, okay? Now, what is my main F on this side? I've got 150 sine of what? Of 60 degrees, okay? So you put that into your calculator. What is 150 sine of 60 degrees? It's going to give me a 129,90, okay, newtons. So that is your F1y, okay, for this side. Hence, I've wrote it on the side for F1. And then I go to F2 as well. I did the same thing. I said for F2y, okay, it is equals to F2 sine of theta, okay? Now, what is my F2? Remember, we've calculated it in question 1.1, and we found it to be 202,7, okay? So it's 2002,7, okay? Let me check if I wrote it the way we calculated it. Yes. Okay, so now it's going to be sine of 68 degrees. Okay, so now what is 202, comma 7 sine of 68? And the reason why we are saying 68 is because if you say 90 over here minus 22 degrees, it's going to give us 68. Okay, 68 degrees that is. So the answer over here is going to be 185 6,87. Okay, let's just double check the ones that we had over there. Okay, so remember we had said, just want to double check our answer here so that we know we've got the correct force for F2. We had like cos 68 which gave us a 0.37, and then 75 divided by 0.37, which gave us a 202. This is what is missing in here, a 202, not 2002. So it's just a minor clinch over there. 202. Let me use the same pen. 202.7. Okay. Yeah, now it makes sense. Okay, because we couldn't have other force being ridiculously high, whereas the other one is not as high. Okay, coming back here to where we are using it. So we are correcting this part to say it's 202, not 2002. Okay. 202.7, which means that we need to correct this one. Okay, so now we have a 202.7 sine of 68. That's it. Okay, that's more like it. So it's going to have 187.94 newtons. Okay, don't forget this is our F2y. So pretty much what we've just did is that we've calculated the vertical component of either of the two forces that are going up. Now we need to equate them. We need to find the resultant force of the two. Now because both of them are acting upwards, meaning that they are on the same direction, okay, both of them are going to be positive. Okay, so now what do we do? Okay, so we've got 129. On this side, we say we've got the F, okay, vertical. I'm just going to say F vertical average or net vertical. I think that sounds better, because we're trying to find F net going up. F net vertical is going to be equals to F1y plus F2y. Okay. F1y, which is going to go back, it's 129.90. Okay, here is the number that I'm taking it from. Okay, here is my F1y. So it's 129.90 plus 187.94. Still remember this one because we firstly got it wrong. Okay, so the total or the sum of these two vertical components therefore give us the net or the net force of the vertical components. Okay, so 129.90 plus 187.94 is giving us a 317.84 newtons. Okay, remember this is not what we are asked. Why are we even doing this in the first place? Because now we're trying to find all the forces that are acting on the vertical so that we are able to find the mass of the object. Okay, so now that we know that the object is not falling down, the object is not moving up, now we should be able to find it because we are equating these two forces, the one that is acting on the upwards and the one that is acting on the downwards. So at the top, we've got your F net vertical being equals to your Fg, which is your gravitational force. Okay, let's just go back to the diagram a little bit. So that means from the center of the object downwards, there's a force that is acting there, which is your gravitational force. And then upwards, there are forces that are acting onto the vertical due to the fact that we've calculated the vertical components. Okay, so that is what we've done. Now, what is our F net vertical? Okay, first, before we even do that, this then will be F net vertical is equals to mg. Why are we saying mg? Because we know gravitational force is equals to the mass multiplied by the gravitational force. So obviously here we've got 3. Let's write it clearer. We've got 317,84 equating to the mass of the object. So what is the mass of the specific object? We are not told. It is what we are trying to find out. So we keep it as it is. So we've got a mass here. However, we do know the gravitational constant that is 9,8, okay, which is the gravitational acceleration. So 9,8, okay. So now we are left with our unknown. Our unknown is what? The mass of the object. Because we're not looking for m 9,8, we're looking for mass, which is your m in this case. So we divide by a 9,8 divide by a 9,8. Okay, so that, let's use a different pen, so that this 9,8 cancels that 9,8, and we are left up with m on the other side. Okay, let's maybe write this closer to here so that we're able to write our number, and we say, what is 317,84 divided by 9,8? It is giving us a 32,43. We never leave it like this. Your alphabet should be on your left hand side, and then your response, or rather your numerical value, should be on the right hand side. So that is why over here we say, therefore m, or rather the mass of this object, is going to be equals to 32,43 kilograms. Okay, so this is how it's done. I'm going to go through it slowly on how we answered this question so that we are able to see what is it that we should be doing for question number 1. Let's first look at the question, what it said. It said two forces, F1 and F2, keep the object of mass m stationary as shown in the diagram below, and then we're given the diagram. So both these forces are helping in keeping the objects of mass m to be stationary. F1 is having 150 newtons in magnitude, acting at an angle of 30 to the vertical, and F2 acts at an angle of 22 degrees with the vertical. Okay, so the angle between the angle that we are most interested in, it's the one that is acting to the horizontal, so that we are able to use it to calculate, to do our calculation. The first question was saying calculate F2 using the horizontal component F1 and F2. We want to find the magnitude of F2 by using the components. Okay, so what we needed to do there, because we needed to remember that these two objects are keeping the mass to be stationary. Okay, so it's not moving to the left or right per se, but then now they're helping it. So that means that the horizontal component of either side are equal. If I'm able to find for F1x, I'm able to know what for F2x will be. So hence that is why we said F1x is equals to F1 cos of theta. Okay, therefore it's we know that F1 has the magnitude of 150, cos of what? Cos of 60. Okay, cos of 60, because if we go right back, this is your 90 degrees angle, and if we say your 90 minus that 30 degrees, then we are left up with what? With 60, because these two angles will then give you 90. Okay, so we continue to say, okay, this is 75 newtons. So our horizontal component for F1 is therefore 75 newtons. Okay, we say F1 is therefore equals to F2x. Mind you, not the original forces, but the horizontal component of it, because now it is not moving on either side. Okay, so that, why are we saying that? Because the horizontal forces are what? They are balanced. Okay, so now we are able to say F2x is equals to F2, which is your cos of 68. Okay, we know F2 because we've calculated F2x because we've calculated F1x. Hence, we have your 75 over here, F2 cos of 68 degrees. Therefore, we say, okay, we have one unknown. How do we then find our unknown? What is cos of 68? It is giving us a 0.37. So we're not looking for F2 0.37, but we're looking for F2 only, which is the main force. What is the magnitude of that one? Therefore, your F2 is therefore 200 and what? 202. Remember, we corrected this one to be this. This is what? 202,7. And then you do your math, and therefore it's giving us F2 being 202 newtons. Okay. With your second question, it was saying calculate the mass of the object. Okay, the mass that is hanging. Remembering that there are forces that are acting onto the vertical. Okay, so we needed to calculate the vertical components of either side, F2 as well as F1. So we needed to calculate F1y as well as F2y. Hence, we did this over here so that it is visible why we are doing it in this case. So this will be your F1y and this will be your F2y. Okay, writing it in dotted so that you remember that it is the component of the main thing. So we're using sine when we're using the vertical, or want to find the vertical component. So F1y then gave us 129,90, as well as F2y gave us what? 187,94 Newton. However, these are two separate. We needed to find the net force of the vertical component. So we needed to add them up. Why? Because they are all, or both of them are going in the same direction. Okay. Hence, we said F net on the vertical. This is my vertical, indicating that it is going up. F1y plus F2y giving us 129,90 plus a 187,94. Therefore, it's 317,84. Okay, newtons. Now, because now there's a force that is going up and there's a force going down. So both these forces are equal to each other because the object is not going up and it's not going down, falling down. So that means these two forces must be equal to each other. Hence, we said F net vertical is equals to mg. Okay, why are we saying mg? Because we know Fg is equals to mg. Okay, 317,84, and then we have our unknown, which is the mass of the object, and times by 9,8. Okay, then we did our maths, and then we have 32,43 kilograms. Okay. Let's move on to the second question over here. They're saying a block of mass of 50 kg rests on a rough surface as shown in the figure below. Remember what I mentioned to you about reading the information that is given to you so that you are able to answer your question the way it should be. Okay? Because most of the answers are just there in your statement. You just need to read them, you need to understand them. Okay? For example, the word rough or the words rough surface, they indicate to you that there is frictional force, that there is. Okay? And goes on to say, when the force F is applied on the object at an angle of 35 with the horizontal, the block starts to move. Okay? The normal force experienced by the block is the 1/3 of the gravitational force acting on an object, and then the coefficient. So these are values that are given to you, okay? And the coefficient of static friction is 0,4. Okay? Remember, the coefficient of friction, it's telling you about the roughness of the surface, the type of the surface that you have, how rough it is. Okay? So here's a diagrammatic representation. So you've got your block, of 50 kg, and then you've got your force that is there, and then you have your 35 degrees. Okay, let's move on to the questions by the help of this one. So the first one is saying, determine the static, define the term. Oh, wow, I can't wait to determine. Now, we are defining first of all, because by knowing the definition of a force, we are able to apply it, or to be able to calculate it, to be able to draw it, should we be required to draw it in a free body diagram or a force diagram. Okay, remembering that your force diagram is uses a representation of a box to indicate any object there is, and then your free body diagram uses a dot, okay, to represent any object. You could be talking about a car, if you're talking about a calculator, so all of that is going to be represented by dots. And mind you, all the forces are moving away. If you're talking about the free body diagram, all the forces are moving away from the dot. But anyway, we're going to put it practical for you so that it is clearer, okay? But right now, what we are doing is defining the term static frictional force. So it is a type of frictional force that acts between two surfaces when the object is static, means stationary. Okay, so let's have our solutions on this side. So this is our solutions for question 2. Okay, so for 2.1, static, let me just, because you're already given that it's as the frictional force that acts, okay, between two surfaces. When the object is stationary. Okay, so remember, definitions are very important. They tell us whether you'll be able to draw the force and be able to calculate it properly. So question 2.2, draw a free body diagram. Free is a representation of any object, okay, including the box that we give in this case scenario, but we're representing using a dot. And all the forces that are acting into this object needs to be drawn away from the dot. Okay, so your arrow should be pointing away from the dot. No arrow or should be pointing into or towards the dot. Okay, so showing all the forces, draw the free body diagram showing all the forces that are acting onto the block when it is about to move. Okay, so remember what the hint I've given you is that the mark allocation for the free body diagram or force diagram or whatever that is asked to you, either or, if they say 4 marks, it's usually an indication that there are 4 forces. Okay, 4 marks is 4 forces. Okay, so that means whenever you're thinking of drawing and then maybe you draw 3, you should know that there is 1 that you are missing. Okay, so let's draw it nicely. Let's look at the diagram once more. So there's a diagram in which we are drawing the free body diagram 4. Okay, so 2.2, free body diagram, that means we've got to represent everything by a what? A dot. Okay, why do I have it slightly up? So it needs to be somewhere here so that all my forces are visible. Remember that they don't give you, like, you can draw as big a dot as you want as long as it's visible and I can see it there. Okay, so because the object is resting on the surface, okay, so or rather it is on the surface, so that means there is normal force. Okay, because by definition your normal force is a force that the surface exerts onto an object and it is perpendicular to the surface. Okay, If there's a surface, then there is normal force. Okay. So here's our normal force. So we say Fn to indicate your normal force. It is a force. What types of force? Normal force. And then because all of this is happening inside Earth, so there is force of what? Of gravity. So you're going to have Fg. Why? Because Fg, or rather gravitational force, it is the force that the surface or the Earth exerts, not the surface, the Earth exerts on an object, and it's always going downwards. Okay? So here's your gravitational acceleration, or rather force of gravity. And then we've got the applied force that is moving in this direction. So you've got your Fa. Okay? And then you've got your frictional force. The things that you need to remember, that the sizes of or the lines or the length of the arrows that you draw signifies the magnitude of that specific force. And then the arrowhead signifies the direction in which it is into. So in here, they're saying when it's about to move. So it's not moving as yet, but it's about to move. So all of these forces will be likely the equal in magnitude. Okay? Why? Because now we've got your F over here, you've got your frictional force over here, you've got your gravity over there, and then you've got your normal force over there. Okay? So even though we don't draw it in scale, when it is about to move, so that means all those forces should be more or less equals to one another. Okay? Because now if the object was already moving, accelerating, therefore it means that one force, which is your applied force, will be bigger than the other forces. Okay? So this is my frictional force, even though let me just write it here so that I know that it is visible for you as well. So 4 marks for 4 forces. Go back a little bit. So you've got your 2.3. Calculate the maximum static friction now force experienced by the block. Okay, the maximum static frictional force experienced by the block. So you need to know the formula. Even though the formula sheet is always given to you, you should know how to calculate the frictional force. So that if you know it, you know what variables then therefore affect your frictional force. Maximum static frictional force experienced by the block. Okay. So you've got your 2.3 over here. Frictional force, what type of frictional force? It is your static. Hence, I put the S there. Static frictional force is equals to mu s times n. And what do we know about n is that it is half, or rather 1/3 of the gravitational force that we are told. Okay, where am I taking this from? It is 1/3 of the gravitational force. There it is. So we know what to do. Okay, so let's put it into action. What is your mu s? Remember, let me just go back a little bit. You've got your coefficient of static frictional force being given to you as what? As 0.4. Okay, therefore over here you've got your 0.4. Okay, multiply by 1/3. Why am I saying 1/3? Because it's 1/3 of your normal force. Remember, your normal force is equals to what? Your Fg, which is equals to mg. So therefore, it's going to be what is your mass of the object. It is 50 kg. And what is gravitational acceleration? It's going to be 9.8. Okay, so therefore you put the other side in your calculator and say, what is 1/3 of this 50 multiplied by your 9.8? So it's going to give you 163. okay, comma 33. So there's a lot of 3's there. You just round it off to the next 2 decimal places, and then you drop down the 0,4. Okay, so what is your 1,6? So 0,4 multiplied by 163,33. It's therefore giving us what? 65,332 newtons. Okay, so that's how simple it is to calculate your maximum static frictional force experienced by the block. Okay, now calculate for your 2.4. Okay, calculate the minimum force required to move the block. What is that force that I need to put into this object so that it starts to move? Okay, remember, when the object now will be moving, it will be moving away on the horizontal. Okay, but as it stands right now, that my block is stationary, so the amount of force that I should be putting in, I need to be able to equate the two. Okay, so what will that tell me? Let's just do it 2.4 over here. So our static frictional force is this one. It's just here on the horizontal. Because this one is acting at an angle, so I'm not interested in the going up of the objects going up or down, but I'm more interested in the moving horizontally. So between the two components, your vertical component as well as your horizontal component, which one will be responsible for your horizontal movement? Your answer is it will be your horizontal component that will be responsible for your horizontal movement. Therefore, I need to say the Fs in here as it stands, because it's stationary, it is equals to the horizontal force that is on the other side. So Fs is equals to what? It is equals to Fax. Okay? Now, how do I calculate the horizontal component of this applied force before we even got into substitution? So we're going to say Fs is equals to Fa, okay, cos of theta. Okay, now I'm substituting because I've already expanded everything there is over there. So your static frictional force is given to as 65,332. Okay, is equals to, okay, Fa is what I'm looking for, that minimum force that is required for it to be able to start moving. So it will be F, then cos, okay. Okay, let's just go back a little bit so that we get the angle in which it was acting on. So it was cos of 35 to the horizontal. Okay, so cos of what? Cos of 35 degrees. Okay, so you put it into your calculator. What is then cos of 35? Is giving you a 0, so you have your F over here and then your 0,82. Here you still have your 65,332. Okay, so you're looking for the Fa, which is that force over there, your applied force. Therefore, what we need to do is divide by 0,2 either, or sorry, on both sides, so that 0,82 can cancel each other. So you're going to have a 0,82 on this side as well. Why are we doing that? So that we are able to find the magnitude of your Fa. So that will cancel that one. So now we have to say 62,332 divided by 0,82 is therefore giving us what? 79. 79,67 is equals to, here over here we're left with the force that we want, the minimum force that needs to be applied. So you remember what I told you? You leave the letters on your left hand side as well as your values on the right hand side. So we say therefore FA is equals to 79,67 newtons. Okay, this is our newtons to be very much clearer. Okay. Right. So I hope this was nice to do, and it was very, very easy to do. I'm just going to round up, and we go through a question again, and we go through the answer on what we did, so we are all on the same page. Okay, let's just go back a little bit. So this is the question 2 that we are doing. A block of mass of 50 kg rests on the rough surface as shown in the figure below. When the force F is applied, remember the F is not given to us, okay? When the F is applied, then the object at an angle of 35 degrees to the horizontal, then the block starts to move, okay? So once this force then is applied, it then begins to move. So the normal force experienced by the block is the 1/3 of the gravitational force acting on the object, and the coefficient of static friction is 0,4. Nice diagrammatic representation is given to us, and then here's your 50 kg block. Here's your force that is not given in terms of its magnitude, and then it is acting at an angle of 35 to the horizontal. Okay. First question, we had to define what a static frictional force is. It is a type of frictional force that acts between the two surfaces when the object is stationary, because the word static is giving us the key that the object is what? It is stationary, so it is not moving. Right. And then 2.2, draw a free body diagram showing all the forces acting onto the block when it is about to move. Hasn't started, it's about to move. Okay, so we had to draw 4 forces because there is a 4 marks, because we likely that 4 marks is an indication of 4 forces. So if you had like 6 marks, so you had to like draw 6 forces that are acting onto that object. Okay, where is our free body diagram? It is right here. Free body diagram, representation of any object of concern by using what? A dot. Okay, so here is my dot, and here is my F, and here is my frictional force. Okay, because it is specific in this case, this is my static frictional force. It is force of gravity as well as my applied force at an angle. Okay, because there's an angle of 35 degrees to the horizontal. Right, moving on to question number 3 and what it said. Calculate the maximum static frictional force experienced by the block. Okay, how do we then, you ask yourself, how do I calculate static frictional force? Ask yourself no more. We said frictional force is mu s multiplied by the normal. Remember that they said that it is the 1/3 of your gravitational force. So that is why I said 1/3, 50 times 9,8, because this is our FG. Okay, this is our FG, because N is, okay, let me just say FG over here, because in this case, so that you are not, okay, so but it's 1/3 of it multiplied by the 0,4, which is your coefficient, giving us a 65,332. Okay, and then the last question, which is R2.4, calculate the minimum force F required to move the block. So how much of a force should I have to be able to move the block? Okay, now Fs is equated to the horizontal component. Okay, because now for it to move, it will not fly or jump up and down, but because there's a surface, it will move on along the horizontal axis. Okay, Fs is your 65, which you've calculated over here, 65,332, is equals to Fa cos of theta, because we want to find the horizontal component of it. So your Fa is what we are looking for. Cos of 35 will give us a 0,82. Okay, therefore we divide by 0,82 on either side so that we find the force that will be just enough to just for the box to take off. Remember now, what we are having is that your minimum force that will be required for the box to move needs to be bigger. Okay, needs to be bigger than your static frictional force over there. Okay, so that the box then will move. Okay, so let's look at this one over here. So it's pretty much, if you get the feel of it, it's pretty much a collaboration of frictional force together with the components, resolution of components, whether it's your horizontal component or your vertical component. It differs from what is asked of us. Okay, so here's our question 3. Now question 3 goes on to say, Charles pushes a lawn roller along a horizontal lawn. Okay, so it's like he's cutting the grass. Okay, he applies a force of F of 700 newtons on the angle. Okay, in the direction of the axle. Okay, it's going in that direction. Now the angle makes an angle of 30 degrees with the lawn. Okay, so that means that to the horizontal, and then friction cannot be ignored. It's actually what's helping Charles to be able to cut the lawn or the grass. Okay, so diagrammatic representation of what Charles is doing over there. Okay, giving us that angle, and then here's the force that he's applying at the axle. Okay, at the angle of the axle. So the first question over here is saying, draw a free body diagram of all the forces that are acting on the stroller. 4 marks. What does that mean? It means that there have to be 4 forces that are applied to this axle that Charles is using. Okay, so draw a free body diagram of all the forces, because now, let me just draw it here so that we are able to see it, and then we can do the other questions on the other page. Okay, so this is the solution for 3.1. And I'm going to put a dot over here. A nice big dot so that a marker can see it. So there is a surface. So there is normal force, because normal force, it is the force that the surface exerts onto the object, and it is perpendicular to the surface. Okay, it's a force that is perpendicular to the surface, in which the surface is exerting a force onto an object. So because there is a surface in here, there is my Fn, and then gravitational force. I'm going to increase my dot. Here's my Fg. Okay, Charles at an angle of 30 degrees, so it has to be away from. So this is Fa. Okay, because it's the force that is applied by Charles, okay, to the lawn roller. Okay, and then we've got what? Frictional force. Okay, because Charles is actually moving this thing. So here's your frictional force. Mind you, even though I hadn't put or use a scale to draw these lines, but they need to be able to say something about what is happening, or the situation, okay, or the problem that is given to you. Meaning that Charles is pushing. It's actually the moving. So that means the magnitude of the line for the applied force has to be bigger than the one for what? For the frictional force. Because frictional force is a force that opposes the motion of an object. It is parallel to the surface and opposes the motion. If Charles is moving to the west, therefore your kinetic friction, kinetic because now the roller is moving, okay? So it is going to the what? To the east, okay? So there has to be that. The markers should be able to tell if the object is stationary or if the object is moving. Okay, so we're making the applied force bigger, so we know that okay, this object is therefore moving in result of the what? Of the applied force being applied onto the object. Okay, so this is how we draw it. Remember, errors are very important. So this is pretty much 3 marks, because you just need to draw the what? the length of these forces. You have to represent them nicely. Okay, so the arrows need to be there, because a force, to remind us, a force is a vector quantity. Now, a vector quantity is a physical quantity that has magnitude as well as what? As well as direction. So this is giving us the length of this arrow, is giving me the magnitude of it. And the arrow is telling me about the direction. Where is it being exerted on? Okay. So we are done with question 3.1 when we said and we had to draw a free body diagram. Remember, free, we are representing any object of interest by using a dot. Okay. So 3.2, calculate the vertical component Fy of the 700 Newton force that Charles applies. Okay. Here's this is the force that Charles is applying. So it's Fa is equals to 700 Newton. Okay, so we need the Fy. So over here, you just needed to remind yourself, okay, if I'm calculating a vertical component, am I using cos or am I using sine? Okay, so we are doing 3.2 right now, and we're going to say solution for question 3. Okay, so our 3.2, Fay, why am I saying Fay? Because it's the applied force by Charles to the learner, okay, grass cutting machine that he has. So it's Fa, then because we want to find Fy, so it has to be sine theta. Okay, this is 700 sine, and you check the angle to the horizontal that we have, so it's 30 degrees. What does this say? Okay, it says that we should do 700 sine of 30 degrees is going to give us 350 newtons. So that is our Fay. Right. 3.3, that is how simple it is to calculate your vertical component. Okay, let's go back a little bit so that we check out the next question. It's saying Charles now turns and pulls the roller. So he's no longer pushing, but is pulling, okay, along the lawn with the same magnitude. So it's the same 700 newtons at the same angle, which is your 30 degrees to the horizontal. What effect does it have on the magnitude and direction of Fy? Okay, that was calculated in question 3. So whether he is pushing or pulling, whether this will there be a difference, or in terms of whether the force that is being applied is a pushing. Remember, a force is a push or pull. Okay, so will there be a difference when he's pushing as compared to when he's pulling? Okay, so the answer is no, because you'll still be able to calculate what? Your vertical component, because the question is saying what effect will it have on the Fy? Okay, so it will be the same. Okay, because if it's pulling, so it's still Fy will remain the same. So we're going to have, as it is pulling, Fay will be equals to what? To 350. Why is that? Because now we need to explain in terms of that. Because the variables that are involved in calculating your Fay, it is Fay is equals to the main force then sine of theta. So the main things that are important in here, it is your angle we said that it remain the same. Okay. Also, the magnitude of the force, it is remaining the same. Therefore, this one will remain the same. Okay. And then our last question, is it easier to pull or to push the roller? Explain your answer. Okay. So let's get the difference in, because what it will make it easier for pushing and pulling, or what will give us a hint on what will be easier between the two, is the friction. Okay, how big the frictional force will be. So the bigger the frictional force that is opposing the object, okay, or the motion of the object, the harder it is. Because if you have a bigger frictional force, then this machine or this grass cutter will move slowly. But if now the frictional force is smaller, it will be easier to just move forward. Okay, so for your 3.4, we say F, which is your frictional force, is equals to mu. Let's just make it a K, for in this case, N. Okay. Now, when this is just for calculating frictional force, but now when let's start by pushing. Okay. I want to draw a diagrammatic. Okay. We said we're starting with pushing. That means the arrow in here is over here. Okay, because he's pushing. This is Charles pushing this loaner at the angle of what? Of 30 degrees. So, what is our normal force in this case? Normal force in this case will be Fn is equals to mg, okay, because we're saying Fn, let's just say mg, let's just start by saying Fg minus F sine of theta. Okay, so that means for us to be able to calculate the normal force, okay, it is the gravitational force, which is what? Your mg minus, okay, the vertical component, because both of these forces are going in a vertical direction. Okay, so minus F sine of theta. So the value that you will have here for your normal force, which is directly affecting your frictional force, okay, will be lower. Okay, but in the second instant, here is still the grass cutter for Charles. However, but now in this case, Charles is no longer pushing, okay, but is rather pulling the object. Okay, so my arrow is here, right? So the way I'm going to calculate my normal force is going to be affected, because now my normal force is going to be equals to Fg, but I remember there's an angle of what? Of 30 degrees in here. So they are now the gravitational force subtracting the vertical component. Okay, so it's going to be, because now I'm pulling it away, it's going to be minus F sine of theta. So what is my Fg? My Fg is therefore equals to mg minus F sine of theta. Okay, therefore my answer in here, because I'm pulling away, is going to be low. Okay, fix a smaller mistake over there, because now here I am pushing, I'm adding to the system. Okay, over here it's going to be positive. Let's just correct it in there. making this one to be high. Okay, so what does this mean? Because now I'm adding to the system, it's going to be my normal force, which is affecting how I calculate my kinetic, okay, frictional force is going to be affected because it's going to be more, because I'm adding the gravitational force together with the what? With the force of gravity. In this case, because I'm pulling away, so I have to subtract the vertical component, making it to be a low value. What does this mean and why are we mentioning it? Remember, we're trying to answer, is it going to be easier to push or to pull? Now, if we have in our equation there, which is FF is equals to, let's make it kinetic, mu K N. If we have a higher value for this, therefore, it's going to increase friction. Why? Because when this one increases, it will make the kinetic frictional force to also does what? To increase. Okay? So, making it harder to move. So, in conclusion, what are we saying? We're saying that this has a direct proportion to what? To the frictional force that there is. So we want to have, for us to be able to move freely or with easier. So we want to have less frictional force over here. So where, in which scenario would it be? It will be when we are pulling. Okay, so our conclusion is therefore it is easier to pull. Okay, that is the first thing, because we are asked in terms of, will it be easier to push or to pull? Okay, why did we say pull? Because when we are pulling, we are subtracting the what? The y component of this of the applied force that is acting onto it. So what is the reason having this to be easier to pull? It's because we're going to have less magnitude of the normal force. Okay, because now if we have a bigger normal force, that means the friction will be more, making it harder to move or making it harder to propel forward or to move, because there's a lot of friction. But if there's less friction, it will be easier to move. Okay, let's run through the questions once more. Charles pushes a lone roller along a horizontal lawn, and then he applies a force of F as of 700 newtons in magnitude on the angle in the direction of the axle. Now the angle makes an angle of 30 degrees with the lawn, and then friction cannot be ignored. Okay, so the first question we asked, we had to draw a free body diagram. Okay, then reminded each other how it should look like and what are the things that we should bear in mind whenever you are drawing a free body diagram. Now, in your 3.2, calculate the vertical component of your Fy of the 700 Newton force that Carl applies. Okay, then we had to remember how it is done by saying F-A-Y, F-A sine of theta, giving us a 700 sine of 30, giving us the magnitude of 350. Okay, 3.3, Charles now turns and around, pulls the roller out the lawn, same magnitude, same angle. What effect does this have on the magnitude and direction of Fy? That was calculated in 3.2. Okay, so we said that it is going to be the same. Why? Because the angle is remaining the same and the applied force, which are the two variables that are very important when calculating for Fy. Okay, and then the last question said, is it easier to pull or to push the roller? Okay, explain your answer. Okay, so we needed to remember the fact that the force that affects whether it will be easier to pull or to push is your kinetic friction, okay, or your frictional force. So how do we calculate our frictional force? It is Ff is equal to mu K N. Okay, so there's normal force that is there, because now Charles is pulling and pushing. this machine at an angle, so we need to subtract the vertical component of it. Okay, meaning if Charles is pushing at an angle of 30 degrees, that means that we need to add the vertical component, which is F sine of theta. Okay, remember Fn is equal to Fg plus the F sine of theta, making the normal force to be more. Okay, in this case, when we increase the normal force as it increases, it's directly affecting the frictional force. However, on this side, when Charles is on the other side pulling, okay, so that means it is pulling, therefore we need to subtract the vertical component, okay, making our Fn to be what? To be smaller. Okay, we need instances whereby it is smaller because we want to make it easier, okay, to move the grass cutter. Okay, so in the pulling instance, so we're choosing pull because what we have is smaller, and this having a smaller magnitude of the normal force is going to make the frictional force to be less, make it easier to move forward. Okay, let's look now at question number 4. Okay, a boy pulls his young sister in a cart with a pulling force of 350 newtons. The rod makes an angle of 30 degrees with the horizontal. The mass of the girl and the cart is 60 kg. The coefficient of friction is mu k is equals to 0.32. And then the first question, calculate the magnitude of the normal force of the girl and the cart. Okay, now we're putting into practice how to calculate the normal force, just like the previous question that we discussed on question 3.4. Okay, so we want to find the magnitude of the normal force of the girl and the cart. Okay, let's find a blank page so that we are able to do solutions for question 4. Okay, let's look at 4.1. Okay, our 4.1, therefore we're calculating the magnitude of the normal force, and then Fn is equals to mg. Okay, because the boy is pulling away or is pulling. Okay, so therefore we need to what? Subtract the vertical component. So it's going to be minus F sine of theta. Okay, so let's look at the values that we have. We have a mass of what? So the mass of the girl and the cart, it is given as what? A 60 kg. That's, yeah. Okay, let's go in here. So we're going to say this is 60 multiplied by a gravitational constant of 9.8 minus the force that is applied. So it is what? It is 350. So it's going to be 350 sine of 30 degrees. Okay, you find the solution of the either side by using your calculator. So it's going to be 60 multiplied by 9.8. So it is given as 588 minus, what is 350 sine of 30 degrees? It's going to be 175. Okay, so what is 558? 588 minus 175 is giving us a 413 newtons. Okay, so this is the magnitude of the normal force of the girl as well as what? The cart. Okay, so and then calculate the frictional force experienced by the cart. Okay, that is our 4.2. Frictional force we've got, because now the boy is actually being able to pull and moving with this with his sister. So it's going to be FFK is equals to mu K N. Okay, in this case, we've already have the normal force, so we don't need to put it in the, or to calculate it first simultaneously with the second one. So what is the coefficient that we are given? Okay, give a coefficient of 0.32. So you get 0.32 multiplied by 413 newtons, which is your normal force that you've calculated in here. Okay, so what is your 0.3 multiplied by 413 is going to give you 123.9 newtons. Right. Let's go back a little bit. Right. And then, which type of frictional force is present here? So what type of frictional force is present here? Because the cart and the girl is actually being moved due to the fact that the boy had applied a pulling force of 350. So they are moving. This makes it to be a kinetic frictional force. Okay. Okay. And then question 4.4, it's saying define this type. What type of frictional force is this? Okay, so it is the type of frictional force. Let's just have a 4.4 over there. It is frictional force. Sorry. That acts between the two surfaces. Two surfaces when the object is moving. Because the word kinetic means movement, okay? Means that an object, it is moving, okay? Let's find out if there is a question that we did not answer, okay? Let's run to the top and then run through all the questions and go through it again to get the feel of what we did. So it says, question 4 is saying, a boy pulls his young sister in a cart with a pulling force of 350 Newton. The rod makes an angle of 30 degrees with the horizontal, okay? The mass of the girl and the cart is 60 kg, okay? The coefficient of friction is mu k. Remember what I said about reading the statement that is given to you? Because a lot of information that they put in there for you to be able to use, okay? Making your calculations to be very easy. Now, 4.1, calculate the magnitude of the normal force of the girl and the cart, okay? Because now the boy is pulling the girl and the cart at an angle of 30 degrees, okay, to the horizontal. Therefore, there is the vertical component to it. Because now you are pulling it, that means you need to be subtracting the vertical component of it. So what did we do? What we do in here is that Fn is therefore is equals to mg minus f sine of theta. Okay, so that means that your mass is your 60 kg. Remember that we are told that the mass of the girl and the cart is 60 kg. We multiplied by the gravitational acceleration of 9.8 meters per second squared, minus the original force in which the boy is pulling the girl as well as the cart, which is your 350 sine of 30 degrees. Okay, because that's an angle to the what? To the horizontal. Okay, so 60 multiplied by that 9,8 gave us a 588, and then minus 350 sine of 30, which gave us a 175 newtons. Okay, subtracting the two, we have a normal force with magnitude of 413 newtons. Okay, second question, we had to be like 4.3, calculate the frictional force experienced by the cut. Okay, so we already had a normal force, because now our formula for frictional force is saying Fk is equals to mu Kn, and then 0,3 multiplied by 413, which we already calculated at the top, then giving us a frictional force of 129. What does this say? It says that the frictional force is smaller than the applied force. Hence, the boy is able to move. Hence, there is a frictional force, that is a kinetic frictional force, because there is movement. Okay, he didn't try to pull them and they remained stationary. They actually moved. Okay, why am I saying they actually moved? Because Fa was equals to 350 newtons, and then frictional force was equals to 123.9. You'll see that the frictional force is actually less. It's opposing the motion of an object. However, it is not stopping the boy from actually moving in his own direction in pulling the sister together with the cart. Okay, 4.3 said, which type of frictional force is present here? Because there is frictional force due to movement. Okay, so it is a kinetic frictional force. Define the type: frictional force that acts between the two surfaces when the object is moving. Okay, you know I always give you your own. I never disappoint, because I know you always want to work. So here's your activity that I want you to do for me in practicing what we've done today together. Okay, it is your question 5, because I've done question 1 up until question 4. So your question 5 is catered for you. Okay, so the first one is saying define the term static frictional force. What do you mean by the term static frictional force? Okay, 5.2, a box full of clothes, mass of 45 kilograms, is at rest on a horizontal floor. The coefficient of static friction is 0.45. Okay, so 5.2.1, draw a free body diagram to show all the vertical forces that are acting onto the box, and it's 2 bugs, 2 marks, 2 forces. Okay, that is a good hint. And then 5.2.2, calculate the magnitude of the minimum horizontal force that is needed to move the box. Okay, so the magnitude of that force that we'll need so that the box then start moving. Okay, the total for this question is only 8 marks. Okay, and then the next one I want you to try out is the one that says a force of 48 newtons is applied to a cement bag, mass of 50 kg, which is at rest on a rough horizontal surface. Okay, remember, read the statement that is provided to you. Highlight, underline the key concepts. What does rough horizontal surface mean? What does at rest mean? All of those things will give you a clue on how to best answer your questions. Okay, the force makes an angle of 35 degrees to the horizontal on the verge. Okay, and the block is on the verge of moving. Okay, now there is a nice diagrammatic representation of what they're talking about, and then 50 kg, here's your 48 newtons of the applied force, which is applied to the bag of cement and then acting at 35 degrees to the horizontal. First question on your question number 6, it says define the term frictional force in words. Okay, not static frictional force, not kinetic frictional force. What is a frictional force? Before you can get into the types, draw a free body diagram of all the forces that are acting on the 50 kg bag. Okay, calculate the magnitude of the normal force. Okay, for the 6.3.1 frictional force, calculate the magnitude of the frictional force. And 6.3.3, calculate the magnitude of the coefficient of static friction. Okay? Hope you find it fun. Hope you enjoy it. And hope you find it doable. So I want to end today's lesson by a quote by Mary Peace. It says that sometimes things are unclear right away. That's where you need to be patient and persevere, and see where things may lead. Okay? Sometimes things aren't clear right away. That's where you need to be patient and persevere and see where things might lead. Okay? Even if it's not clear now, even if it's not clear once you have your first attempts, but believe in me, as you keep calculating, as you keep practicing, it will soon be clearer. Okay? Keep on working on these calculations that we did. Do your activity that I've given to you. It will be much clearer. Not at first, but eventually it will be. Okay? Thank you for attending today's lesson on frictional force as well as resolution of force into components. Okay? See you next time.